Yeah, let's get started. Today we are very excited to have Yunju here to give us a guest lecture. And Yunju Li is an assistant professor of computer science at UIUC. And before joining UIUC, he collaborated with Feifei Li and Jiajun Wu during his postdoc at Stanford. And Yunju got his PhD from MIT, co-advised by Antonio Torba and Ross Tetrick. And Yunju's work has been recognized through the Best System Paper Award and the finalist for Best Paper Award at the Conference on Robot Learning, CORL. And his research has been featured by a lot of media, including CNN, BBC, the Wall Street Journal, Forbes, Economist, and MIT Technology Review. Okay, without further ado, let's welcome Yunju to give us the guest lecture.
Thank you, Ganya, for the kind introduction. And I'm really excited to be here to give this guest lectures on the topic of learning structured world models from physical interactions and for the robots to do better physical interactions in the real world. And the goal of today's lecture is that by the end of today's lecture, you'll be convinced that we should add structure to our learning systems. And with a suitable choice of structures and models of the environments, we'll get much better sample efficiency and generalization capabilities for real-world manipulation tasks. Some examples, as I'm showing here, including the manipulation of granular objects, deformable object, fluids, as well as there's an example of making dumplings using a lot of different tools. So start with the motivation. The question is, how far are we in achieving human-level robotic manipulation capabilities? We have already seen a lot of examples, especially in the drones or self-driving domains, where the robot has been on par or sometimes surpassing human capabilities, like, for example, the Boston Dynamics humanoid robots performing backflipping. And also, for example, in the self-driving, although we haven't seen a massive deployments of self-driving cars in our daily lives, the field has progressed a very long ways over the past few years, and we have seen some robot taxis in San Francisco. But we are still very, very far away of achieving human-level capabilities in performing physical interactions with the environment. There are just some typical examples people currently deployed in the industry, where the robots typically focusing on relatively simple pick-and-place tasks for objects with relatively simple shapes. But we humans can do much more than that. We can crack eggs, spread butter on a piece of bread, making dough, and making sushi. All of these capabilities goes far beyond the reach of the current robotic systems, where humans is interacting with deformable objects, with objects with high degrees of freedom. We're also making long horizon plannings of doing a tasks that requires multiple steps. We also know how to correct from errors. For example, if things go wrong, we know how to correct our mistakes and getting back to the correct path. And I would like to argue like one of the key enabling factor and also one of the key gaps between robots manipulation capabilities and humans manipulation capabilities is this intuitive models of the world, where we humans can effortlessly predict how the environment is going to change if we apply a specific actions. For example, looking at these two examples, although we humans are manipulating objects of different materials, one is dough, one is a pile of onion pieces, we can predict intuitively how the dough will deform and how the onion pieces will move around. And it's exactly this kind of predictive ability that allows we humans to plan our behavior in order to achieve a specific target configuration. Here is how the system generally works. For example, we have the world. The world is give this kind of planner some observations, and this planner is trying to plan some action to execute it in the world. And this planner internally has these intuitive models. These intuitive models takes the current observation and action as inputs and trying to predict how the environment is going to change. And this predictive model can help the planner to plan its behaviors in order to change the state of the world to the agent's desires. So in order to make this kind of predictive model, there are generally two ways of doing it. The first one is to learn the model from data, which we can roughly categorize it as model-based reinforcement learning, and which I'm pretty sure has been covered a lot also in this course. The general framework of model-based reinforcement learning, especially model-based reinforcement learning from visual observations, work like this. Where you have some visual observations, or you map these visual observations into some latent representations of the environments. There could be some kind of supervisions you apply to this latent representation, like reconstruction loss, to making sure this latent space Z captures some meaningful information about the underlying state. Then you neurodynamics model over this latent space to predict the evolutions of these latent vectors. It has advantages like, for example, directly learning from partial observations and handle cases where the underlying dynamics is uncertain or unknown. We have a lot of success stories, like, for example, Mu0, as well as controlling robots from pixels. But a lot of existing work only considers Z as the one single dimensional latent vector. It is very unstructured and actually limited in terms of generalizations. For example, looking at these two examples, like dough or pile of coffee beans, when human looking at them, we're not just thinking of them as one single latent vectors. We have a good understanding about the structure, about the compositionalities of the systems, and it's exactly this kind of structured understandings of these objects that allows us to model the dynamics of objects with this kind of complicated physical properties. Talking about the structure, the other way to build the dynamics model is based on physics, our understanding of the physical laws of the environment. And this is arguably the most compact way to encode the structures into the systems. And it has excellent generalization, like F equals MA, it generalizes. And we have successful stories, for example, in humanoid robots from Boston Dynamics, as well as for the rockets. In these scenarios, the humans spend a lot of efforts, engineering efforts, to build a good mechanical models for those robots and rockets. And we use this model to plan the robot's behavior. But these routes typically assume that full state information is available. We assume we know everything about this robot, what it states, what is joint angle, what is joint force, etc., etc. We assume we know those informations. This is obtainable for robots that are designed by us. We design the humanoid, we design the rockets, so we can assume we can get those information from engineering practices. But in the real world manipulation tasks, especially in cases where we face partial observations, full state estimation and full parameter estimation sometimes becomes very hard and nearly impossible. For example, in cases of manipulating a pile of onion pieces, estimating the states and of each and every one of the onion pieces is very, very hard or nearly impossible. Or in cases, for example, buttoning our shirts, we humans only have to know the local information before we can button this shirt. But if we want to use a physics-based model, we typically have to use the full state information of your clothes before we can simulate this buttoning process. So both methods have their pros and cons. On the left is model learning. On the right will be structures in the model. So the work I'm going to present today will try to get the best of both worlds, trying to learn models with structures inspired by our humans' understanding about the structure and dynamics of the environments. And we can use this kind of structured models of the environments to plan the robot's behaviors. And one thing I want to highlight here is that we learn the model from data. And this model has its internal structures. This will give us a much better sample efficiency and generalization capabilities compared to like pure end-to-end, like unstructured model learning. And it's much more flexible and adaptable to partial observations and environments where we don't know about their dynamics compared to, for example, physics-based models. Let's make the problem a little more concrete. Here is the optimization problems we want to tackle. This is our objective functions, like cost function C, defined over the observation Y and the action U. And we want to come up with this policy, for example, pi, to minimize this objective function. And there are three very critical constraints we have to think when formulating this optimization problem. The first one is perception. Essentially, this perception module maps the observation Y into some representations of the environment Z. And then is the dynamics module. The dynamics module takes in the current representation DT and the action UT, and to predict how the latent vector is going to change into the next time step, DT plus 1. And the third constraint will be this policy constraints. We want to derive this control signal from the current representation Z. And if you look through these three constraints, you realize there is one very important decision variable we have to make in terms of designing the systems, which is the representation Z. The design and the choice of this representation Z has a profound impact in determining the overall structures and the overall formulations of this problem. And we have to think very carefully on what kind of representation we should use to represent the environments and what its implications about the system structures. And I will show later, a right choice and a suitable choice of representation and structures can achieve much better sample efficiency and generalization capabilities. Again, if you have any questions, yeah, please.
Like why the perceptions of function U is just for general notations? It actually function U in practice.
It doesn't have to necessarily rely on the U. It's just a formulation that's trying to be as general as possible. So typically, when we obtain the current representations, we not just consider the current observations. We're considering a history of observations. Obviously, this sequence of Y will contain history information. But if you provide some additional information about what leads to the changes of Y by providing the actions, which can give you some additional information.
So I can replace the U1 to T by Z1 to T. Z1 to T minus 1.
Yeah, assuming you can like infer those Z's from some inverse dynamics model, like they are containing some similar set of information. Mm-hmm.
I have a question.
Mm-hmm.
Can you use the future information from future observation to infer the current state with the T with one to capital T?
So there has been a lot of practices that also use future observations to obtain a better estimations of the current states, because some information in the future might be helpful for have a more complete and precise estimation of the current states. But it's just when you want to use this model in the real world for manipulation tasks, you don't know what will, you can predict what's going to happen into the future, but you don't know exactly what happens that in the futures. So you have to rely on current and past information to make the inference. Yes, there are some causal relationship in the temporal directions. Mm-hmm. Question?
So by including the action variable in the perception equation, aren't you like inducing an inherent bias for like finding ZT? Because then like if your action, like if your all the actions still now aren't based on the perfect ground truth, which they aren't, then like you would be trying to find ZT which is not optimal, right? Because your actions themselves were not optimal, for example.
Here, the U doesn't have to be optimal. So the U can be some history observations, and as long as, because if you just based on the current observation, for example, some still images, it's very intuitive to know that you don't know, for example, the velocity informations. So that's why you need some history information, where the incorporation of the actions can give you some additional information in like what type of actions that cause the changes of the observation Y. And because here we assume like we have a robot, and the robot is executing those actions in the environments, and those actions are commanded by humans. So we can typically assume we have access and know what use we applied into the environment. Mm-hmm. Question? Mm-hmm.
So if we don't know currently we don't know the future, we would always do prediction, right? Can we do the other way, like using some privilege estimation or privilege methodology during training to represent the Z, and then during deployment we can just take those information out, but just leave those useful information.
Yeah, that's an excellent idea. So during the training, if you are doing some, for example, sim to real transfer, and during the in the simulations, like you have privileged informations and you know the full state information about the environments. And that full states can help you to train some, for example, teacher network or some kind of network that leverage the privileged information. But during deployments, you want to make sure your systems can take in raw observations of the environments in order to actually do some interesting interactions in the environments, to do some online planning of what the robot is going to do. And another, like one way is to do sim to real transfer, where simulation can give you some privileged informations. Another way is also to learn from the real environments. But during the training process, you assume you know the futures. And if you know the future, you can obtain some additional information, for example, how the systems is evolving, which sometimes with a good system design can give you better estimates of the current states. For example, estimation of the tracking information over times. And those information can be used to train your models. And that's information doesn't necessarily have to be there during the test times, but they are used to obtain the supervisions to train the model. Thanks. Okay, I'm gonna continue. So today's lectures, we're gonna focus on the representations of particles. Particle essentially is a very fine-grained representation that decompose the objects into a bunch of particles. You can imagine it to be a point clouds. Or the rigid objects can be decomposed into particles, deformable objects, clothes, ropes, fluids. They can all decompose into a bunch of small spheres. And we have the particles describing the overall geometry, which also describes the interactions within an object as well as between the objects. And particles, you could actually imagine it to be like nodes within a graph, and the edges of the graph describing the interactions between particles. And in order to model the dynamics of these particle systems, we are using graph neural networks. And we call it graph-based neurodynamics model. And here is how it in general works. Here is a graph containing 3 nodes and 3 directed edges. And our state Z, again, remember this representation Z, essentially is a union of the node sets as well as the edge sets. And for each edge, for example, pointing from node B to node A, we have an edge encoder that's taking the information from the sender B and the receiver A to derive some representation EK for that specific edge. And then for every node inside this graph, for example, node A here, we will aggregate all the representations on edges where node A is the receiver. And the information will be aggregated together to obtain some aggregated message information that passed into the node A. And then we will feed the information together with the information on node A into a node encoder to derive the updated node representation. And then we can define the objective functions between the node representation to whatever quantity you care about, or between the edge representation to whatever quantity you care about to supervise the whole graph neural models. And here, what we care is the evolutions of the environment, essentially how the states will change, how the node will move around over time. So the supervision here will be the mean squared error between the predicted next states, A hats, as well as the actual next states like A. We want to minimize their distance by optimizing the parameters in the node and edge encoders. If you notice, here is a very important structural design for this kind of models, where the node encoder is shared among all nodes and the edge encoder is shared among all edges, meaning the parameters you need to optimize in the node and the edge encoders doesn't scale with the size of your systems. It only scales with the number of types of edges and number of types of nodes in your systems, which nicely integrated this kind of structural inductive bias that allows you to do very simple, efficient learning, as I will show later in the experiments. And also, for example, for objects of different materials, you could actually have like different structural design. For example, for rigid objects, instead of using like a plan or fully connected graph, we actually build a hierarchical graph to allow more efficient message passing. We'll also only predict the global motions to enforce its rigidness. And for deformable objects, we'll also use hierarchical modeling, but we'll only predict local motions to allow the particles to deform freely. And for example, for fluids, we'll use dynamic graph building, where the particles only connect to neighboring particles. And as time changes, the neighborhood also changes. So the graph will also be adapted accordingly. We'll also only predict local motion to allow the fluid particles to move freely. And on the right will be our neurodynamics model long horizon rollouts, where the inputs to our systems will be the states of all particles at the first frames. It will be able to predict long horizon into the future and maintain the relevant constraints, like the rigidness constraints for the rigid objects and the incompressiveness and density constraints for the fluids. Here are some additional results. On the left, is the ground truth. On the right is our model's open loop future predictions. Again, the inputs are the initial position and velocities of all particles. Here are two fluids fall down and merge with each other. Here's another example where we have this two cuboids to mimic the fingers of a parallel grippers to deform a deformable form. Here's another example of shake a box of fluids. On the left is the ground truth, on the right is our model's predictions. Here, we assume like the container is fully actuated, where we move the containers around and we're predicting the motions for the fluids. Like I said earlier, because the node encoder and edge encoders are shared among nodes and edges, you can naturally generalize to systems that are larger than during training. For example, here to show that our system can generalize to environments that contains 2 times more particles than during training, and it correctly captures the wave of the fluids in our model's prediction. So this is about prediction, but our goal is never only about prediction. Our goal is always about how we can use this model's predictive ability to help the robot to do interesting manipulation and planning and control tasks. Here, we leverage the fact that the learned model is naturally differentiable. So we can just using off-the-shelf deep learning packages like PyTorch or TensorFlow to extract gradients from the learned model. And these gradients can help us to do the trajectory optimizations to synthesize the action sequences. And we can also use model predictive controls to correct the model's prediction error. Here's how it works. Let's say our current state will be this Z0 showing blue dots. Our goal shows in this red dots. And we have some initial guess of what our action sequence could look like you here. And our model will make our predictions. And the predicted state is labeled as Z hat, capital T. And we can define some objective functions measuring the distance between the predicted states and the goal. And that loss function's gradients will be propagated back, trying to optimize the values for our action sequence. And we can do it iteratively to getting the model's prediction closer and closer to our target's goal. And this is typically referred to as the shooting method in robotics. And it has a lot of problems. And the first problem is that what if your model is not perfect? So the model may not be accurate enough. So in this case, we'll apply a model predictive control framework where we only execute the first action U0, and the environments will give us a new state Z1. And we will re-optimize the actions U using gradient descents to account or compensate for the model's prediction error. And another question?
Curious, when you're trying to differentiate your learned simulator, how can you make sure that your first order ingredients is the same as the original? It's like when you do the training, you're only matching the next state rather than the coding.
That is a very good point. So the learned model is essentially a proxy and approximations of the environments. So it can never be guaranteed to be 100% perfect. So not only the gradients, but the forward prediction can also have error. Like even if the forward predictions is maybe sometimes accurate enough, the gradient itself may also sometimes have a lot of like local optimums, locally may not be smooth enough compared to, for example, the actual dynamics. So there are methods that are trying to not only supervise the model through forward prediction, but also supervise the model by using informations from the gradients to make sure both the forward prediction and the gradients matches the original simulators or some kind of physics-based models. But in reality, in practice, what we found is that for different systems, the usefulness of the gradients also varies. If the system itself is reasonably smooth, the gradients can be very useful. If there's a lot of discontinuities in the dynamics models, the gradient may not be as useful. So that's why a very key enabling factors is not just relies on gradients, but also use samplings as the tools to account for some local optimal. Yes, here you can consider both first order, second order, or even zeroth order like optimizations. Yeah, for example, one of the key enabling factors for the success of this method is to use GPUs, where you can do the sampling and also gradient descents simultaneously for hundreds or even thousands of trajectories at the same time, or even like tens of thousands of trajectories, depending on how large your model is and how long of a horizon you want to do the plannings for. But this kind of parallelizations on GPUs can significantly improve the practical use of these methods in the real world for practical problems.
How can you combine the first order solution to the zero solution?
This is again a very good question. Like in practice, there are a lot of different ways of doing it. So one very straightforward way you can imagine is that you can have some canonical action sequence. And based on this canonical action sequence, you can sample a lot of like sequences around that canonical action sequence. And you do gradient descent for each and every one of them simultaneously. And so each one will do some kind of local adjustments to make it better. And after the adjustment, you will aggregate the optimization result by evaluating the objective functions. And the aggregated actions will be your neo-canonical action sequence. Yes. So they nicely complement each other. For example, sampling can help you get around some local optimal, but in order to do some very fine-grained like local refinements, your gradient can be very useful. So in practice, there's a lot of like different design of the algorithms. Like you can take a deeper look if you are interested. For example, coarse entropy methods or model predictive path integral, MPPI, or the method from your professor's lab, this COBOL MPC, which also address some of the problems in the current MPPI method. So if you're interested, I encourage you to take a deeper look, which are very handy tools for you to use if you have this model. And these tools not only work for neurodynamics model, but if you have a physics-based dynamics models, and if your tools, if you want to try, or if the problem is amendable to zeroth order optimizations, those are also tools you could consider. So here are some of the results. Here, our task is to shake this box of fluids. And our goal is to shape the shape of the fluid to match the target shown on the top left. And because the fluid it cannot be stabilized, it will just fall down. So we want to achieve the target shapes when the countdown goes to 0. And here is the control process, and here's the results. And here's another example where we shake a box of fluids, and the resulting fluids will match the targets. And as you can see, the dynamics modeling capabilities is really the key to help the models to plan its behaviors, to control the position and velocity of the containers in order to achieve the targets. Here's another task where we are using this parallel grippers to deform this deformable object to achieve the target shape shown on the top left. And here's another example. Here the decision variables are the position, orientations, and gripping distance of this parallel gripper. Here's the result. And we also deploy these systems in the real world. Here to show like we can have this real robots deform this real form in order to like change its shape to match the shape shown on the left. And here's the result.
In those slides, is as a grippers model as a special node in the graph, and is that how you model the edges, the force? Is that how it works?
This is also another very important like questions and very important designs you have to consider in this environment. So it's like, how do you incorporate the environments? Because the particles not only should like take into account the object itself, you should also take into account the environments as well as the tools used to interact with that object. Here we are also using particles to represent the tools. And here, because we don't assume we know the force information, because the force information is very hard to obtain in the real world, unless you have some tactile sensors that can transfer tactile information into the force informations. So in this case, we are just like setting the actions as the positions of the particles in the next frames, like what you plan the grippers to do, and we will move the particle to that specific locations, and we will integrate that into our design of the overall graph. Okay. So to summarize a little bit about this work. So the reason we can do the real world experiments is to actually do sim-to-real transfer, where the model is learned from a physics-based simulators called FLEX, amazing simulators and developed by NVIDIA. And to transfer the learned model to the real world, there are two key things to consider. One is the perception. And in the real world, we have depth cameras to do a 3D reconstructions of the deformable form, and we'll be able to sample particles within the surface of this within the sample within the surface of this deformable form. And because the physical parameters can be different between the simulation and the real world, we'll also do some online adaptations to estimate the parameters for the deformable form. But we do not have a physics-based simulator that can simulate everything around us. So we are asking the questions, can we remove the dependency on the physics-based simulators and directly learn the models from real data? Ideally for far more complicated tasks beyond just like grouping the form to change it to some simple shapes. So given the fact that I'm already working on this elastoplastic objects, and I'm also from China, so we're asking the question, why not making some dumplings? Why not push these directions further all the way through and to tackle some of the more complicated challenges in the domain? So dumpling making is actually an extremely challenging task and involves a lot of like different steps along the dumpling making process. Specifically, first we have to make the dough, and to make sure the dough is in like a nice physical state. And then we, for example, have to roll the dough in order to make some like thinner structures for the dough. You want to cut small pieces out of it. And then we'll have to use tools, for example, to flatten the dough into a large enough areas such that we can have these circular shapes in order to warp stuff around. And then we'll put, for example, these fillings onto the dumpling skins and then trying to like close the skins in order to make this dumpling. If you look at these steps, you realize how challenging it is if you want to have a general purpose robots that can also do these tasks. And during this process, there are not only just hands involved, there are also some other tools that are involved. That meaning not only that is long horizon, but involves the reasoning about what type of tool to use, and given a specific tool, what specific action to take in order to make progress. So for this purpose, we design robots manipulation systems where we have a general purpose robot arm equipped with a series of 3D printed tools. And those 3D printed tools are designed by drawing inspirations from the everyday tools we might encounter in our daily life. For example, the grippers, the rollers, as well as, for example, presser punctures of different sizes and shapes, as well as we have cutters, a knife cutter, as well as circular cutters, and also spatulas to move things around. And last is a hook that trying to, for example, interact with the with the tools and other objects in the environment. And some of these tools actually involves actuations, meaning it can, for example, open and close the grippers, and the rollers can also roll back and forth. And also some other tools that with fewer degrees of freedom. So those tools are also designed in a way that when we close and open the grippers, some of the tools will also move together as the gripper closes and opens. And those tools are being put together to constitute this kind of robot manipulation systems, where we have like 15 different tools in the peripheral of these robots, where the robots can just pick and place those tools back and forth. We also have 4 RGBD cameras looking at the environment, look at those in the middles. And here, the red area will be the robot's working space in order to interact with the dough. And here, I'm gonna show the manipulation process of these robots to interact with the dough to make a dumpling out of it. So before I play this video, there's one very interesting thing I want to highlight is that there will be a human constantly perturbing the robots from doing its job. And you will be able to see like how the robot is robust to this kind of external disturbance. Here, the robots first cut the dough, and the human just go there and place the dough back. The robot knows it has to cut the dough again to get the right volumes outside of the dough. And the next steps will be, for example, the gripping, trying to grip the shape into some like regular shapes before it's trying to like flatten it. And the humans also constantly goes in and perturbing the robot from doing its job. The robot is making its real-time decisions at what specific tool to use and what action to take. What specific tool to use, meaning it is making decisions at a discrete level. And also given this kind of discrete choice of the tools, the robot is also making decisions on what specific action to take in order to progress into the next stage. Here the human just is so annoying, trying to also like add small pieces to it or fold the dumpling skins, and the robot knows how to make progress. Here is since is the most interesting. After robots cuts a circle out of it, the human shows no mercy, destroy everything. The robots knows, okay, I have to get back and start from scratch. This really shows the patience of these systems in performing these actions that is robust to external disturbance. After that, the robot will push the peripheral like skins away, and then using a spatula to move the dumpling skins onto this dumpling clamp. And then the robots will go there and place dumpling fillings onto the dumpling skin and close the dumpling clamp to make these dumplings. And again, for some of you who know the dumplings very well, this is actually a very sad dumplings. A dumpling with very thick skins and very small fillings. But here I want to show you that this is an extremely challenging long hardened tasks. And this is so far the state of the art of using a general purpose robots that can use a general purposely designed tools to do these tasks. Of course, there's room for improvements, and I'm definitely encouraging you to think about how to make improvements upon that. So now let's dive into the method. So like I said, the robot has to first decide what tool to use, and which is correspond to this task level planning. To do this task level planning, the robot systems will take the current observation and the targets as inputs. And we'll have a classification network trying to predict what specific tool to use at the current stage. For example, currently the robot might predict, I want to use a large rollers in this case. And then given these predicted tools, the robot is also making motion level planning, meaning this continuously decision makings on what specific action to take. And this policy network will take in the predicted tool and also the current and target configurations as inputs to predict these continuous actions that needs to be executed in the world. And these executed actions will lead to a new state, and these new observations will be feedback into the systems to close this perception and action loop. So that's why we can be robust to external disturbance. And at the core of this motion planning learning stage is again this neurodynamics models, where this dynamics models is exactly the same models as the model you see in the previous work. It's just this time this model is learned purely from real world. There's no simulation involved at all. The model is learned from real world interactions. And this model is conditioned on the current tool as well as action. It takes in the current state as input and trying to predict the particle states and how the particle state clouds will deform into the next steps using this tool and these specific actions. And then this predicted states will be fed into these objective functions. These objective functions will try to predict like what specific, okay, I think there's a mistake here. This is actually the policy network. So this is a mistake. This policy network takes in the current state, the target state is one, where you want the models to go to, as well as a tool in trying to predict this kind of actions. And this actions is compared with the actual actions that leads to the changes of the state from S0 to S1. And you compare the distance between the predicted action and the actual actions. And their difference will be taken into account, and the gradient of that will be back propagates into these policy functions and trying to predict what specific action to take. And again, the core of this is also this graph-based neurodynamics model. You can imagine it to be a simulators or generative models, depending on what background you are. And this model can help you to generate data. And this generated data will help you to learn this kind of policy network, trying to predict what specific action to take given the current observation. And here, I'm just showing some more visualizations of how the dynamics model works and how the dynamics model's prediction look like. For example, given the current observations, here is how we are representing the environment. We have the blue dots, blue particles, represent the shape of the dough, as well as the red particles describing the shape of the tools. And here is actually our asymmetric tools trying to grip this dough. And Here, what I'm showing will be the side-by-side comparisons between our model's predictions and the ground truth. The first row is a prediction, and the second row is the ground truth. Here, as you can see, our model predict the changes of the shape of the dough, and it's very accurately matches of what the ground truth look like. Here's another examples of like pressers, and after we press the dough, our model also accurately predicts that the dough shape will be changed, will be flattened as you execute this action. Here's another example of, for example, like rolling, press and rolling, this kind of rollers, and our model also predicts that the shape of the dough will be enlarged. And one key things I want to highlight about this model learning, this learned model, is the fact that we only require 20 minutes of real-world interactions per tool in order to learn a very decent dynamics models for that specific tool. This is because we're using this graph neural network. Again, goes back to the earlier point I make, where the node encoders and edge encoders are shared among all nodes and all edges. So this nice structured inductive bias gives us this kind of very simple, efficient learning process, where just 20 minutes of real-world interactions, you can learn models that is noticeably more accurate than the state-of-the-art physics-based models, even with extensive system identifications, as I will show some quantitative results later. Like, because these nerd models, like question?
So, like, how do you know that is like set up from that to your representation for graph?
This is also a very good questions. You ask very good questions. So these are very important design choice you have to make in how to transform the visual observations into a set of particles. Like for example, how many particles do you sample and how do you sample? Because depending on the sampling, specific sampling strategies, the distribution of the particles can also be very different. So in this case, for the tools, you can see like the tools particles are very regular because we assume we know the shape of the tool. So we can sample the particles uniformly over the surface to constitute the shape of the tool. And for the particles on the object, on the dough itself, we use farthest point sampling to making sure we have sufficient coverage of the shape of the overall dough. And here, the number of particles, we do operation studies. And to see like what is the right, the sufficient number of particles such that you can give like good prediction accuracy, but not too many particles that makes the computation less efficient. Does that make sense? Thanks. Question?
How can we matching those particles between the frames and making those particles consistently so that we can compute the state laws?
That is another good question. So in this case, instead of using a mean squared errors that assume tracking information over time, because our model only learns from real interactions, so there's no tracking. Actually, the dough is a textureless object, which is actually very hard to track. So in this case, the supervision, instead of using mean squared error, which assume tracking, we actually use a combination of chamfer distance and earth movers distance. Then instead of like measuring the movements of particles at the individual particle level, we measure the changes of the overall shape. So earth mover distance and chamfer distance are the specific type of loss that measures the overall changes of the shape instead of only as instead of tracking individual particles. So that loss is used both for training the model and also to measuring the performance of the planning results. Any other questions?
Yeah, two nuanced questions. One is, seems like learning from simulation doesn't hurt, right? So why in this project you guys didn't like warm up the new like from simulations? Because it's impossible to simulate the dough, I guess, or yeah.
So the motivation of this work is the fact that we don't have a simulation. They can simulate everything around us. So we are asking the questions, can we learn the model pure from real interactions? This is actually how we humans do things. We humans don't like constantly calculating F equals MA in our minds. We have this intuitive models in our mind. We learn this model from our humans' physical interactions with the environments. So we also want to have the same capabilities for the robots by learning direct from real interactions. And of course, you can warm up the models using simulations, but we compare with the state-of-the-art physics-based simulation techniques called material point methods. As I will show later, the models, the MPM model, material point method model, even with extensive system identifications, the model is noticeably less accurate than our learned model because there's no sim to real gap. it's real-to-real transfer.
And when you train the policy, it seems like can I view the policy as inverse kinematics? So you're trying to predict what kind of action gives you what kind of consequence?
Exactly. You can imagine this model is essentially a forward model that predicts what's going to happen. Planning is actually an inverse process. Given the currents and some targets, you want to come up with the actions that derive that's target that leads to this target states. So we use these forward models to do this inverse learning process of distilling this kind of like policies through this kind of data generations and policy learning procedure.
And then here's a question: is like, why don't we do previous sampling-based approach with the learned model to planning, and we directly predict the action?
Good questions. That's the first thing we tried. We use sampling-based approach. I wouldn't call it doesn't work. It just takes a lot of time to do the sampling. Because this particle, this is a graph containing like hundreds. We have 200 to 300 particles representing the dough, and some additional 1 to 200 particles representing the tools, depending on the size of the tool. So there's a lot of particles, and you have to do a lot of message processing within the graph to do like future predictions. So that is very expensive to do online sampling. So that's why instead of doing online sampling for the action for the trajectory optimizations, we learn our policies.
Gotcha.
Do you have some to use these action primitives?
Yes, we use action primitives. Like I said here, here is the action, for example, for this roller, the action primitives will be how far you go down for pressing and which directions and how far you roll forward. So we use action primitives for each tools. And action primitives used both for data collections and also planning.
Thank you.
Mm-hmm. Okay, so one question.
At this time, how do you generate the targets with the subgroups?
So the sub goals are this again a very important detail, very good questions. The sub goals are actually, for example, if you see the video here, the bottom row you can see like a sequence of tools that seems already there. So these are provided by humans. The specific sub goals are not like automatically generated by these robots, which is impossible to automatically generate all the sub goals for this such a long hard task. Possibly. This was done like a little more than 1 year ago. So back then the foundation model hasn't been that powerful. I think definitely it's possible. But here we humans actually like do the tasks for 10 times, and we collect the intermediate states, and those intermediate states are used to train our tool classifier. And we also know this kind of state machine based type of how the task is progressing. Essentially, we have this sequential state machines, which where the robot is deciding how to jump forwards and whether now is the time to jump forwards and whether I have to jump back. So this kind of tool classifier allows this system to jump back and forth over this kind of sequential state machine. Mm-hmm. Question?
Yeah, so few times we saw that like the human was putting a small mass of dough, right?
Mm-hmm.
And the robot was like just pressing it over again and again. So is it possible to like reason about like not just the shape but also the mass of the object which the robot is interacting with? Because like at the end, I think you said that the dumpling is really hard skin, for example.
Yeah. So for this specific task, because like if you see something here, after it cuts a circle out of it. So like before it reaches that stage, the volume itself is not that sensitive for the success of the method, because it will nevertheless remove the excessive part. It just, if it's too much, you cannot have a thin enough skins in order to warp it up. But as long as there's like a room for variations in terms of the mass for the dough, and you are actually right. So there can be some external like monitoring functions or monitoring mechanisms to see, for example, if I want exactly this amount of doughs. So that will require, for example, the depth cameras to capture the, for example, the volume of the doughs, understand the 3D geometries, and understanding this like spatial occupancies to measure its volumes. So that technically can be done. Just we didn't do it because this task is not very sensitive to that. But I can give you another observation here. As you like press or roll the skin to a very thin layer, and the depth cameras actually is very hard at capturing this fine-grained like difference between the distance between the surface of the dough and the surface of the table. So that will make it very hard to have a very accurate measurements of the volume of the dough. You can use better cameras, of course, but if it is very flattened out, it can also be very challenging.
And like, how can we modify this to like do something with the human in the loop? So like, for example, if the human is actually trying to help the robot to prepare something, then like, is it possible for the robot to decide if the human's actions are actually aligning with its goal or?
Yeah, that's a good question, because here in this case, what the robots what the humans are doing, are not like making progress. They are driving the robots back and back to some earlier stage. But because we have this tool classifier, so if the humans is making progress for the robots will recognize that and continue from where the person left out. Thanks. Okay, so because this learned model is not learned just for this dumpling making, although dumpling making is the most complicated task we consider in this work, but this system can also be used to do some other tasks. For example, shaping this dough into some like alphabet letter shaped cookies. Here we shape the dough into different letters that R, O, B, C, and K. The reason we did that is because this word is called robot cook. So we want to use this letter to spell out the name of this work. And here is how it actually works. Here it is trying to make a shape of letter O. It will have this like symmetric clampers to make a round shape for this dough. And then it will use a puncture, like a circular punctures, trying to punch a hole in the center of this dough. Yeah, this will be the results of making O. And here is another example of making a letter K. And if you look at what the robot is doing, you actually feel, oh, this robot is kind of creative. In order to make a K, because it's an asymmetric shape, so it actually trying to use asymmetric tools, like with a pad on the one side and a rod on the other side. And these tools will be able to like make this shape of letter K. So if you ask a human to come up with this strategy, it may not be as straightforward. So we also show like our system, this learned model will be able to generalize to objects of different materials, like the real dough, play dough, air dry clay, as well as some modeling foam. You can all exhibit some decent level of performance of making this dough like this letter like shapes. So here are some quantitative results. One thing I want to highlight is that because we learn these policies, this learned policy allows very sample efficient, like online computational times, and also achieve much higher accuracy when we ask the humans, can you recognize this letter and what letter it is? And we achieve much higher accuracies by these human studies. And there are two key take-home messages. The first one is that policy learning significantly improves the runtime efficiency, because we compare our methods with using sampling-based method, like for example, coarse entropy methods, and our systems use significantly less time, because during the test time, it just like feed forward pass on the policy network to predict the total use and the action to take. And we also compare with the state-of-the-art physics-based model, like material point methods, abbreviated as MPM here. This learned model can be much more accurate than physics-based model, even if we apply extensive system identifications on these MPM models, indicating the flexibility of these graph-based neurodynamics models. Question?
What's RL plus GNN and why is it so slow?
So here, like RL plus GNN, we consider a lot of like this kind of learning time, training times of using this model, as well as some alignments with the real observations.
Okay, so the planning time somehow includes like the time taken to train.
Okay, so far what we have seen is these structures that combines particles and graph neural networks to capture the compositionalities of the environments. And it allows the dynamics modeling for rigid objects and fluids, deformable objects like plasticisms and dough, and also shows like very decent predictive abilities for the interactions between the objects and various of different tools. And the learned model will be able to support planning that's a very long horizon, and also planning both at the task level and also at the motion level. So one thing you might notice that is the representations I discussed so far, both for these particles to represent the fluid rigid object, the dough, they are all like graphs that are pre-specified, like the questions we discussed earlier. So the particles are determined by our human intuition or some ablation studies on how many particles we want to use to describe the environment. But I would like to argue that the most effective scene representation might have to be dynamic. Here's a very simple example. If you have a robot, they want to retrieve some objects that are very far away from that robot. When the robot is far away, you only have to know there's an object out there. As the robot getting closer and closer to that object, it has to focusing on more on the local geometry and details for that object before it can grasp it. So depending on the task, depending on the objects, or even depending on the different stages of the same task, the representation might have to be dynamic in order to achieve the best trade-off between the efficiency and effectiveness. So in order to learn this kind of dynamic representation of the environments, we take this object pile manipulations as a test bed and trying to see how we can dynamically adjust or determine the representations for the robots in order to achieve the best trade-off between efficiency and effectiveness. And this granular object manipulation is actually a very common task we might encounter in our kitchen environments or in some pharmaceutical environment, some cleaning environments. So specifically, again, we're also representing the piles as a bunch of particles, exactly the same particles you see earlier. So, but depending on the resolution you want to use to represent the particles, the resulting like particles sets might look different given the same observations. So if you use like too few particles, like 2 to 3 particles, you won't be effective because you won't be able to capture the shape of these piles. You won't be able to like make effective progress. But if you use too many particles, like thousands of particles, it might be inefficient. Like we discussed earlier for the dumpling making work, the reason we neural policy, the reason we don't do online planning is because we have too many particles. Online planning is very inefficient. So we want to find a good representation, and our definitions of a good representations is the combinations of efficiency and effectiveness. We want the representation to be minimal in its capacity, but sufficient for the robots to do the specific task. So this is our key insights, a minimal but sufficient representation, which is the representations we want. So specifically, in this case, we want to derive the representation based on the current state shown on the left, and the target configuration shown on the right, which is the circular regions we want to like gather all the pieces into. And we want to use the abstraction level that is the most effective and maximizing the task rewards. So we want the representation to be minimal in its capacity. So we want to find this, this abstraction level that is minimal, but is effective at doing the task, which is effective at maximizing the task rewards. And we do this kind of optimization using Bayesian optimization. Specifically, given the current observations shown on the left, as well as the target regions we want to aggregate all the pieces into. And on the right will be our Bayesian optimization results. The horizontal axis will be the number of particles we want to use to represent the piles. The vertical axis will be how much we can reduce the task cost. And what you can get is this very nice bell curve. Meaning, if you have a very small amount of particles, it is not very effective at reducing the task cost. But if you have too many particles, because we constrain the time budget the model can be used to do the optimizations, it is also not very effective at minimizing that, reducing the task cost. So we'll be able to find these optimal points in the middle. That is the most effective representations at representing these piles given this target configuration. And given the same current configuration, but if the target configuration is more complicated, like the letter K here, and the number of particles you actually want to use to represent the piles will be larger in order to make the most effective progress. Meaning the same current state, but more complicated target configurations can require more particles. The other way around is also the same and also interesting. For example, given the same target configurations like the circle here, if the object pieces are very spread out, then here is our optimal number of points to represent the pile. But if the object pile is already very clusters and close to the target configurations, you actually need a higher resolution models to represent the pile. The reason for that is that because if the piles is very spread out, a lot of actions are equally good at reducing the task objective. But if the pile is very close to the target configurations, you really have to have high resolution model to review the subtle difference between the shape of current piles and the targets in order to make progress. So that means same targets, but different current configurations might also require different resolutions in order to make the most effective progress. So we collect a large data sets using Bayesian optimization to obtain the labels that contains this tuple, current observation, targets, and the optimal resolutions. We'll do this offline, collect the data sets, and then we'll be able to train a resolution regressor that takes in the current observation and the target as inputs and trying to predict what should be the optimal resolution we want to use to represent the pile. And this predicted resolutions will be conditioned by our perception module that transforms these RGB observations into this graph, this pile of particles. And this pile of particles will also be taken into by this graph-based neurodynamics models. This graph neural networks takes in the current Z, which is a graph, and the actions and inputs to iteratively predict what's going to happen down the road. And one thing I want to highlight is that even if we are using different resolution, we can still using the same graph-based neurodynamics model, as long as this graph-based neurodynamics model is conditioned on the selections of these resolutions. So the same set of parameters can handle difference and continuously choice of this resolution. And then this predicted outcome will be compared with, for example, our goal, and we'll come up with an objective functions. These objective functions will be used to backpropagate the gradients to do the trajectory optimizations and optimize the choice of the action sequence. Again, we are also doing not just gradient descent, but also sampling, a combination between sampling and gradient descent to give us the most effective optimizations for this action sequence. Any questions? Mm-hmm. Mm-hmm.
Yeah, what's the cost function y-axis?
The cost function is like given the current particle representation, given the current resolution, we have a particle representation for this pile. And given this particle representation of the pile, we already have a dynamics model that's learned. We are evaluating how effective it is at using this dynamics model to reduce the task cost. So the lower, the better. Mm-hmm. We do the routing simulation. And we use these simulations to generate the current configuration targets in order to come up with these labels such that we can train a resolution regressor, and that resolution regressor can directly transfer to the real world.
It's from a Gaussian process, is the curve?
Yes.
And is this like the pre-model process and for its the next slide we show the model.
Mm-hmm.
So this is like some analysis.
Okay, that's a very good point. So, because in order to tell the story, it's slightly reversed. So specifically, what we did is this optimization process. This optimization process is using a models like conditional on a specific resolution, and this model we want to measure how effective this optimization process is at reducing the task objective, and that is being plotted here, like how effective it is at reducing task objective. So we first have the model. The model is conditioned on a wide range of resolutions. And given the model, we also have this optimization process. And then we do this. Yeah, so it's just for storytelling purposes. Like I want to show like different resolution will imply like different results given the current configuration and targets. Before I talk about this kind of optimization, but you catch the point. Like the right order will be model learning, optimization, like do the Bayesian optimization in the simulation to collect the data, and then that data is used to train this resolution regressor. And this is the process of actually deploying the models in the real world. You still have questions? Okay. So we evaluated our systems on these robots with the top-down cameras and a wide range of different types of piles of different types of granularities. And here is one task of gathering the piece. You can see like here, the task is to gathering the pieces to achieve the target circles shown on the bottom right of each block. You can see we are dealing with object pieces of a wide range of granularities. Some big pieces like the carrot and candy, and also some small pieces like the rice. You can see this task will involve different type of dynamics depending on what kind of objects you are working with, but the same learned models can be directly deployed to these pieces, no matter it's bigger or smaller, but the same model all work on this kind of objects. Okay, the last push. And here's another examples of pushing these object pieces into achieving some more complicated target shapes. And you will very quickly realize what the target shapes are. And yes, the target shapes are the letter shapes all the way from letter A to letter Z. And this is actually a non-trivial task. It involves some non-trivial redistributions of the object pieces. And also it involves some fine-grained alignments between the object piece and the fine-grained like shapes of the target regions. And the same model, again, the same models is doing all of these tasks. We are not doing any like online adaptations. The same model, the same pipeline, but we just change the objective functions. It can automatically determine the resolutions and conduct these tasks. We also try some Chinese characters. For example, here translates to hello world. So the robot will also be able to manipulate these pieces to achieve these target configurations. And also compare with humans. In order to make the life easier for the humans, we give this kind of overlay between the target configurations and the piles. For the robot, for humans, you have a good reference on like how to do this kind of alignments. The humans can actually do the tasks very well, but there's a very interesting distinctions between how the robot is doing the task and how human is doing the task. If you look at the video again, you will see like human is taking a strategy to do this kind of sequential approach. It will first like align parts and gradually move on to other part of this pile in order to align with the target shapes. But we humans, but the robots are doing it somewhat differently. It is not taking a sequential approach, but a more holistic approach in terms of aligning the overall shape. So this is kind of interesting because it's really depending on what kind of objective functions and what kind of optimization procedures you are using to do the task. And of course, given this kind of low-level gathering capabilities, we can couple this low-level gathering capabilities with some higher-level planners in order to do tasks like rearranging these object piles. Here's the task is to like reverse the locations of these two piles. So we can have some higher-level planners to plan the movements of these overall shapes, and that movements will be taken into account by this lower-level planners in order to push these pieces to those like intermediate sub goals in order to do this task of reversing these two piles. And in the end, it can do the task. So to summarize, the take-home message here that I want to convey is that we use a structure that combines particles and graph neural networks and is particularly suitable for objects with that is compositional or with high degrees of freedom. It comes with two key benefits. The first one, again, is generalizations. It is able to generalize to systems that are larger than during training, like the fluid examples, like 2 times small particles, boom, you can still working on it. And you can also generalize to unseen target shapes. For example, the letter shapes all the way from A to Z. The model has never seen the target shapes like that because the model are generated by randomly like pushing the pieces around. But the learned model, because we are using particles, can also nicely capture the structures of the systems and achieving those letter shapes all the way from letter A to letter Z, never seen during training. The second benefit would be sample efficiency, where, for example, with just 20 minutes of offline interaction data for the DOE examples, we'll be able to learn a very good dynamics model that is much better than the state-of-the-art physics-based models for doing this kind of dumpling making task. And also, you can think about how you can dynamically select the resolutions for your representations to get the optimal trade-off between efficiency and effectiveness. And this thread of work has inspired 2 major threads of follow-up work. The first thread is on using particles as a representation to learn large-scale graph-based dynamics. And here are some works I particularly like from DeepMind, Intel, Stanford's on, for example, do graphics simulations of large-scale particle systems for intuitive physics, as well as for mesh-based systems. Another thread of follow-up work is to use particle as representations for deformable object manipulations, that in the context of, for example, amorphous material manipulations, close smoothing, elastic materials, as well as benchmarks for deformable object manipulations. So in the last few minutes, I want to talk a little bit about some of the future directions you could imagine along these directions. And remember, what we have been discussed is learning these structured word models that capture the structures and compositionalities of the environments that give you generalization and sample efficiency for complicated manipulation tasks. And this was our original formulation. We have our objective and 3 constraints: perception constraints, dynamics constraints, and control. And we discussed about the choice of this representation Z, which is the particles. And at each modules of this overall systems, there are actually ways to make progress. For example, in the perception module, like Guanya has said, like, can we leverage the foundation models, the visual foundation models, to give us better generalizable representations for the perception module. For example, there has been a lot of like recent progress on developing these visual foundation models. I'm sure you are very familiar with like segment anythings or Dino that give you these dense visual descriptions of the environments. And our recent work has been trying to fuse those 2D visual foundation models into the 3D space and obtaining the geometric informations of the environments, as well as semantic descriptions of those environments at different levels of abstraction, like the instance level and the part level. And this kind of generalizable semantic information can help you, for example, track the movements of an object in the real world. For example, like we have discussed earlier, because we cannot track the change of the dough, shape of the dough, we have to use like chamfer distance on Earth Mars distance. But assume that we have very good foundation models. They can track the changes of the states directly based on real visual observations. We can actually directly learn the model using more stable objective functions like mean squared errors to learn the dynamics model. This is on the perception side. There's also this dynamic side. And dynamic sides, we are constantly striving for, can we get even better sample efficiency? Can we get even better generalizations? And there has been, and there could be follow-up like integrations on more physics principles into this modeling structures, like to do some physics informed or physics integrated learnings and estimations of your dynamics model. Here is a very interesting recent work that's trying to combine Gaussian splatting, some like some splatting, also some extended versions of particles, which is Gaussian splattings, and trying to define dynamics models directly based on the splattings that is able to simulate the dynamics of, for example, butters, this kind of sources, and also spreading of this host. But one limitation of this work is that they are actually like hand code the physical rules into the splatting or particle, this type of compositional systems. And the question could be, how can I identify those dynamics models directly from interactions? So this could also be a very interesting directions. And the third direction is on the control side. Like, how can we provide like better guarantees on the safety? How can we provide better guarantees on the optimalities? Because currently, like we have discussed like extensive earlier, like we are currently using combination of sampling, gradient descent, or policy learning. None of them can give you certifications on how well you can do, especially provide some kind of like safety measurements, like meaning how can you make concrete and rigorous claims about your system's performance. Like existing works, most of them relies on sampling, and Guaya's work considers the covariance. But down the road, where I'm thinking about, maybe we can bring even more principled optimization tools that give you those guarantees. And some of those principled optimization tools are not particularly compatible with neural network, because neural network is highly over-parameterized. So some of our recent work consider the task of how we can sparsify the neurodynamics model to reduce the capacity of the model to make it less nonlinear but still maintains a reasonable approximation power for the dynamics, such that we can use more principled optimization tools to provide better guarantees, like for example, mixed integer programming or some other optimization tools. So yeah, I hope this is the overall structure. Question?
This way, like I think it's gonna have a function and
No, there's no. So in the end, so I want just hope you to look at this formulation again to think about how this kind of formulation you can use to in your problems and how you can think of this robotic systems in a modularized fashion and what kind of structures you can incorporate it into the systems all the way from the representation side, from the dynamics, perception, and also the control side. You can ask a question.
Can I send the speaker first?
Okay.
I have two like hello questions. I don't want to ask technical questions, two hello questions. Cool. Yeah.
This is okay. My question for so
I can go to the slides. Mhm. This is actually the take-home message.
Yeah, I just ask one question and then one is that for this model, because we are learning the latent space, right? So I'm thinking about if this is a diffusion model, no?
No, this is not a diffusion model. This is a graph-based model. That's just a feed-forward neural network. Mhm.
Or if we like insert some human terrain into the latent space, such as I remember like the long flow or that kind of idea. So that human could do more alignment or terrain into this latent space to help with that. But I think that could be helpful or
I think that can totally be helpful. So the internal structures of this neural network, there's a lot of room for design. Like for example, previously I talked about the physics integrated, but there are some other structure like diffusion, transformer, those kind of structure can potentially also be integrated into the systems. Transformer also, for example, also consider some compositional systems, which is somewhat similar, have some similar spirits compared to, for example, graph neural network. And different these modeling choices will come up with different kind of benefits. Diffusions specifically is very good at handling, for example, multimodal distributions and is very good at, for example, capturing like different possible future evolutions, which is actually some of the things you could encounter in the dynamics case. For example, you throw the dice, throw some objects, depending on, there's a lot of uncertainties in terms of how the future is going to evolve, and the future evolution can be multimodal, and diffusion can actually be helpful in essence.
Like hello question for everyone here. Do you believe a skill law in model learning? Like how far can like OpenAI Sora, it's kind of large video prediction model go in terms of word model learning? Just curious about that.
Okay.
Do you think data is all we need for a word model for
Data is definitely important. Scaling is definitely important. I wouldn't bet against data and bet against scaling. But I still believe there's other necessary recipes to the overall pictures, like the structure, understanding of 3D, understanding the compositions of the environments. And talking about Sora, like we have chatted yesterday, like Sora is absolutely amazing. So it is great. But Sora, if you want to actually use Sora in the context of robotics, there are several key challenges. The first one is Sora is a text conditioned video generation. It doesn't take into account the action. But you can see all the models I learned is action condition dynamics model. The only way you can use this model to plan the robot's behavior is this model have to take into account the actions. Sora currently doesn't do that, so that limits its applications in robotics. That's the first, I would say, major limitations. The second major limitation, again, limitations for their applications in robotics. The second limitation is this fine-grained controls of the initial configurations or the scene configurations or scene relationships. Like, because Sora is like a text to video, the description of the text is actually a very low capacity descriptions of what you want. And there are a lot of things that are just like automatically imagined through this Sora model. But what if you are facing a specific problems? You have the plates, you have the knife at the specific locations. How can you generate videos such as the plates and knives and whatever forks and salads and peanut butters on a specific location cover specific regions? That level of fine-grained controllability for the current generation models is still not there. I'm definitely looking forward to models that can do that, but I haven't really seen models that can achieve that levels of fine-grained controllability, and that is also a necessary condition for their wide range of deployments in robotics.
Let's send the speaker again. Yeah, and thanks a lot. Yeah.
Thanks.
The meeting.